Welcome to Unit 2 Review. With atomic structure and properties understood, it's time to look at the different types of compounds so we can better understand their structure and properties.
Here we will review the types of chemical bonds, intramolecular force and potential energy, the structure of ionic solids, as well as metals and alloys, Lewis diagrams, resonance and formal charge, and then VSEPR theory and bond hybridization.
In the previous unit, we learned about periodic trends, such as ionization energy, electron affinity, and electronegativity. So we are now ready to find out what happens when two elements come into contact with one another. There are several ways that chemical bonds can form, so let's go over these now.
When an element with a very high electron affinity, like chlorine, and an element with a very low ionization energy, like sodium, come into contact with one another, electron transfer will occur. One atom really wants to gain an electron, and the other has no problem losing one, so the electron is transferred from one to the other, generating two ions. In this case, we would get a sodium cation and a chloride anion. Notice that these each now have a noble gas electron configuration with an outermost shell that is completely full. This is a particularly stabilizing situation, which explains why these atoms will readily adopt these configurations. When cations and anions are near one another, they will interact via ionic bonds. These are strong electrostatic interactions that allow for the formation of ionic compounds, such as sodium chloride in this case, which we know of as table salt. Another way of looking at this is to examine electronegativities. If the difference in the electronegativities of two elements is sufficiently large, above 1.8 or so, electron transfer will occur, and we will get ions that then participate in ionic bonds, according to Coulomb's law. So that covers the first type of chemical bond, but very frequently elements will not transfer electrons from one atom to another. Rather, they will share electrons to form covalent bonds. These can occur between atoms of the same element, like two hydrogen atoms, or between different elements that don't have such dramatic differences in electronegativity, such as carbon and hydrogen, that will share their valence electrons. To get a bit more technical, when a covalent bond occurs, such as with a molecule of H2, it is because the electron from one hydrogen atom feels the pull of the nucleus of the other atom, and vice versa. So it's as though each electron belongs to both atoms. In this diagram, we can see that as the hydrogen atoms approach one another, their 1s electrons begin to overlap, and an ideal internuclear distance is found. That is the distance between the two protons. There is a dip down in energy because if each electron is interacting with both protons, that is a stabilizing and therefore energetically favorable situation. However, if we push the protons too close together, it begins to become less favorable due to proton-proton repulsion, just like if we were to compress a spring, which is why we see the curve rise steeply to the left. It is this phenomenon that reveals the internuclear distance that represents the lowest potential energy, and therefore the ideal covalent bond length between the hydrogen atoms. So we can now describe how a covalent bond forms, but we must understand that there are different types of covalent bonds, and a bond formed between two identical atoms will necessarily be different than one formed between two different types of atoms. Say that we are looking at a covalent bond that forms between two identical atoms, like the bond contained in a molecule of H2, or any other diatomic molecule of one element. In such a case, the electrons will be shared precisely evenly. The two atoms have precisely the same electronegativity, so there is no basis for one atom to hold on to more of the electron density than the other. We would call this a nonpolar covalent bond. If the two atoms participating in the covalent bond belong to different elements, like a molecule of HCl, it might be possible that the electrons are not shared evenly, but rather that the electron density is more attracted to one of the atoms than the other, which we can see is happening because the cloud of electron density is more prominent on the chlorine atom than the hydrogen atom, due to the fact that chlorine has a greater electronegativity. If the electrons are shared unevenly, this is called a polar covalent bond. In a polar covalent bond, the atom that is electron deficient is symbolized with a delta plus, and we will call it partially positive. The atom with the electron excess will be marked with a delta minus, and we will call it partially negative. These partial charges are not formal charges like we find on ions. They just represent the unequal distribution of the electron density in the bond. We can also mark this with a dipole arrow. Here, the arrow will point in the direction of the electron excess, with an additional line on the other end to resemble a plus charge, indicating the side with electron deficiency. So to summarize, when two elements interact, the electronegativities of the two atoms in the bond will tell us what kind of bond will form between them. A polar covalent bond will occur if the two atoms participating in the bond have an electronegativity difference of somewhere between 0.4 and 1.8, as this is a difference that will allow for electrons to be shared, but unevenly between the atoms. If the electronegativity difference is larger than 1.8, the electrons will no longer be shared. One atom will steal electrons from the other, resulting in ions that make ionic bonds. If the difference is less than 0.4, we say that the bond is essentially nonpolar, or pure covalent, where the electrons are shared roughly evenly between the atoms. Another way of stating this is saying that as the electronegativity difference increases, the ionic character of the bond increases, from nonpolar covalent to polar covalent to ionic, or from electrons shared completely evenly to being shared unevenly to not being shared at all. To find out what kind of bond will form between two elements, just consult the table of electronegativity values and calculate the difference. Let's also describe one more type of bond called a metallic bond. The rules we just went over typically apply to bonding between two nonmetals, or between a metal and a nonmetal, but metals also can make bonds amongst themselves, and these are not quite the same as ionic or covalent bonds, but rather they will exhibit characteristics of each. We will think of a metal as consisting of positively charged metal cations, while their valence electrons are delocalized over the entire lattice, which means they are essentially free to move around within the substance. We still regard the atoms as being of neutral charge, but this other way of illustrating the particles helps us understand some of the properties of metals, like their electrical conductivity, as well as malleability, or the ability to bend, and ductility, or the ability to stretch. According to Coulomb's law, we would expect metals that form cations of greater charge to make stronger bonds, as will also be the case for metals with more valence electrons. Metals can also mix together to form alloys. Substitutional alloys form when the metal atoms are of similar size. Here, atoms of both metals are incorporated directly into the lattice structure, participating in metallic bonds. Brass is an example of such an alloy, which is a mixture of copper and zinc. On the other hand, interstitial alloys are ones that form between metals with atoms of different sizes. The smaller one can fit into the interstitial spaces between the atoms of the larger metal, which makes the alloy harder or less malleable. Steel is an example of such an alloy, which is iron with carbon atoms in the interstitial locations. There are even substitutional interstitial alloys, which combine both configurations. Apart from metals, we should also examine the lattice structure of ionic solids. As we know, these form between a metal and a nonmetal once electron transfer has occurred, and the resulting ions form a network of ionic bonds. This three-dimensional structure is called a lattice, and it allows each cation to be surrounded by anions, and each anion to be surrounded by cations, thus maximizing electrostatic interactions. As we would expect based on Coulomb's law, ions with greater charges will make stronger interactions, as will smaller ions that can pack more tightly together. Ionic solids are not malleable like metals, nor do they conduct electricity in the solid form, as their electrons are not delocalized. They tend to be brittle and break apart. They also tend to easily dissolve in water, where the ions can dissociate from one another and become solvated by water molecules, at which point the resulting solution will conduct electricity.
We now know quite a bit about chemical bonding, so we are ready to visually depict groups of atoms in order to find out how they will bond to one another to form covalent compounds. The convention we will use is that of Lewis symbols or Lewis diagrams.
A Lewis symbol will consist of an element's chemical symbol surrounded by some dots. These dots are the valence electrons of that atom. When we place these dots, we typically will use 4 coordination sites, or basically the areas to the top, bottom, left, and right of the chemical symbol, and we will place 1 electron in each location before doubling them up, sort of like Hund's rule. For example, these are the Lewis symbols for the elements in period 3 of the periodic table. You can see how the dots are distributed as we go from 1 to 8 valence electrons, and we can see that up through silicon each electron is alone, and then from phosphorus to argon we begin placing a second electron in each coordination site. If we want to draw Lewis symbols for cations and anions, it's really no different. For a cation, we simply remove a particular number of dots and display the corresponding charge. For anions, we add dots and display the charge. These individual Lewis symbols are what we combine in order to show a Lewis diagram for a compound. If that compound is ionic, we simply place the Lewis symbols of the ions next to each other, such as with sodium chloride here. But Lewis diagrams are much more useful in the context of covalent compounds. If we want to use Lewis symbols to represent all the atoms in a covalent compound, we have to show the manner in which the electrons are shared between the atoms. To do this, we simply need to draw the Lewis symbols for each atom in the compound, and then wherever there are unpaired electrons, atoms can come together to form a covalent bond, as a covalent bond involves 1 electron from each of 2 atoms being shared between them. For example, here are 2 chlorine atoms, each with 7 valence electrons, one of which is unpaired. The 2 atoms come together to form a covalent bond consisting of the unpaired electrons. In Lewis diagrams, instead of 2 electrons sitting between 2 atoms, covalent bonds will be represented by a line. So always remember that any line in a Lewis diagram represents 2 electrons. And we can also have lone pairs, which are pairs of electrons that are not participating in any bonds. Each chlorine atom has 3 lone pairs here. Here are a few more examples of covalent compounds represented as Lewis dot structures. Notice that each pair of electrons in a covalent bond is expressed as a line, while lone pairs remain individual dots. Now let's go over some guidelines. The first of these is called the octet rule. This is the rule that states that certain elements, especially some of the most common ones like carbon, nitrogen, and oxygen, will form bonds in such a way so as to become surrounded by 8 electrons, be they from covalent bonds or lone pairs. This is a condition called a full octet, and it is like achieving a full valence shell, or noble gas electron configuration. For example, carbon has 4 valence electrons, so it will tend to make 4 bonds in order to interact with 4 more electrons and fill its octet. Each covalent bond has 2 electrons in it, so carbon is surrounded by 8 electrons. Nitrogen, with 1 lone pair and 3 electrons, will only need 3 bonds to fill its octet, since one of its coordination sites already has a pair of electrons. 3 bonds plus the 2 electrons in the lone pair equals 8. Oxygen, with 2 lone pairs and 2 electrons, will need 2 bonds to fill its octet. And fluorine will need only 1 more electron and thus 1 covalent bond to fill its octet. Noble gases like neon already have a full octet because they have a full valence shell, which is why they don't make covalent bonds. So these few elements we just mentioned will tend to follow the octet rule, and this will be a good guideline when considering these elements. We should understand that most other elements will not follow the octet rule, like the way that hydrogen only needs 2 electrons to be satisfied, or how elements with access to d orbitals can expand their octets and accommodate more bonds than would be expected. But elements like carbon, nitrogen, and oxygen are the most commonly found in organic molecules apart from hydrogen, so the octet rule applies to a lot of molecules. A result of the octet rule when looking at carbon, nitrogen, and oxygen is that these atoms can make more than 1 bond to one another if they need to in order to fill their octet. Take for example carbon dioxide. If we place the oxygens on either side of the carbon atom, we can see that joining unpaired electrons to form the two bonds will leave some more unpaired electrons. Therefore, we can make additional bonds between these atoms, forming double bonds between the carbon and the two oxygens. Formaldehyde and ethylene are further examples of double bonds. The only way to complete an octet for each atom is for them to share 4 electrons. We can see that if each bond counts as 2 electrons towards the octet of any atom participating in the bond, then all of these atoms will each have an octet. We can also have triple bonds, such as with these molecules. The more bonds there are between two atoms, the shorter the bond length and the more energy that is required to break the bond. As we mentioned, there are many situations in which the octet rule is not followed. There are some electron-deficient molecules that lack an octet for the central atom. Elements like boron and aluminum only have 3 valence electrons, so they can only make 3 covalent bonds. In boron trifluoride, boron makes 3 bonds to fluorine, so it will have only 6 electrons around it rather than 8. In addition, while elements that follow the octet rule will be tetravalent, meaning they will have 4 coordination sites, there are also hypervalent elements like phosphorus and sulfur. These can have 5 or 6 bonds respectively, which exceed the octet rule in terms of the number of electrons that can be found around a central atom. Again, this happens because these elements have access to d orbitals, whereas elements in period 2, like carbon and oxygen, do not. So these elements will commonly make 5 and 6 covalent bonds, respectively. Even xenon, a noble gas, which we would expect to be inert, actually can make covalent bonds with select other elements, such as with the compounds shown here. So we should get used to the idea that the octet rule really only applies to a handful of elements on the table. Sometimes when we draw Lewis diagrams, there are multiple options for how to distribute the electron density within the molecule. These will often have to do with the way that pi electrons are distributed within a molecule, and we can represent the molecule using different resonance structures. First, let's quickly discuss formal charge. An atom will have neutral charge when it is contributing a number of electrons to a Lewis diagram that is equal to its valence. So, for example, carbon has 4 valence electrons, so when it makes 4 bonds, it contributes 1 electron to each and is thus neutral. Nitrogen has 5 valence electrons, so when it makes 3 bonds and has 1 lone pair, it is neutral. If instead it makes 4 bonds, it contributes only 4 electrons, which is 1 less than its valence, so it has a formal positive charge. Oxygen has 6 valence electrons, so when it makes 2 bonds and has 2 lone pairs, it is neutral. But if it makes only 1 bond and has 3 lone pairs, it contributes 7 electrons, which is 1 more than its valence, so it will have a formal negative charge. This is the easiest way to tell the formal charge of an atom in a molecule. To see how this applies to the concept of resonance, let's examine the nitrite ion, NO2-. Say we want to draw the Lewis diagram for this polyatomic ion. Nitrogen likes to make 3 bonds and have 1 lone pair. This means that we could have a single bond to the oxygen on the left and a double bond to the oxygen on the right, adding 1 additional electron to this oxygen here to give it a full octet and achieve the formal negative charge for the ion. Or we could have the single bond to the right and the double bond to the left, reversing the bonding behavior for these 2 oxygens. These 2 structures are precisely equivalent, so which one of them is correct? The answer is that technically neither of them is correct, or at least neither of them accurately describe the true nature of the molecule. It is the case that a double bond is shorter than a single bond, but experiments show that the NO bonds in this molecule are identical in every way, as the molecule is completely symmetrical. This means that the reality for this molecule is somewhere in between these 2 structures, which we must call resonance structures. If a molecule is participating in resonance, it is able to delocalize pi electron density, which means electrons in the form of pi bonds and lone pairs, and distribute these electrons in a way that cannot be represented by an individual Lewis diagram. Instead, it must combine them to form something in between the 2. For example, each resonance structure has 1 double bond and 1 single bond, so the reality is that there is partial double bond character represented by the dashed line on both sides, almost like 1.5 bonds. Shown here is the resonance hybrid, or the composite resonance structure, which more accurately describes how the electrons are distributed in this molecule. An important thing to note is that it is not the case that the double bond is flipping back and forth rapidly, but rather that electron density has spread out to give a partial negative charge along the entire area of the molecule, which we sometimes report outside of brackets, since the charge is not localized on a single atom. Here's another example, the nitrate ion. This one has 3 resonance structures, each of which shows the double bond going to one of the 3 oxygens, with 2 oxygens showing a negative charge and the nitrogen showing a positive charge, giving an overall 1- charge. If the true structure of the ion involves an averaging of these structures, then there must be some double bond character all around the molecule. Once again, although we can look at resonance structures to give us clues about how a molecule will behave, none of these 3 structures actually exist. The reality is the composite resonance structure, which spreads the electron density in the double bond around the molecule, so as to be delocalized around the portions of the molecule that are exhibiting resonance. This may sound strange, but there is overwhelming evidence to support this, from studies that show all of these nitrogen-oxygen bonds are identical, giving the molecule symmetry, and also from the way these kinds of molecules react with other molecules. We should also quickly discuss how to compare the stabilities of different resonance structures for the same compound. There are a few rules with this. First, a structure with fewer formal charges is more stable. So if one structure has one formal positive charge and one formal negative charge, and another structure has all atoms completely neutral, the latter is more stable and thus more strongly contributing. Next, if formal charges must be present, we want to look at which elements possess them. More electropositive elements are better at accommodating formal positive charges, so carbon is better than nitrogen, which is better than oxygen. More electronegative elements are better at accommodating formal negative charges, so oxygen is better than nitrogen, which is better than carbon. If 2 structures use atoms of different elements to bear a formal charge, we can use this guideline to compare them and assess which is more stable. And finally, resonance structures that maximize the number of atoms with a full octet will be favored, and will be more highly contributing due to their stability.
So we now understand how to depict molecular structure using Lewis diagrams, but these are 2-dimensional representations of 3-dimensional objects. We will need to understand molecular geometry as well, and to do this we will use VSEPR theory.
VSEPR theory is short for valence shell electron pair repulsion theory. The central idea of VSEPR theory is that the things that surround an atom, whether they are bonding pairs of electrons or lone pairs, consist of negatively charged electron density, and these areas of electron density will repel each other. This means that the electron domains surrounding an atom will spread out to be as far away from each other as possible. The orientation that these electron domains will adopt depends on the number of them present. 2 electron domains that surround a central atom will find that a 180-degree bond angle is the best way to maximize the distance between them. This will be called a linear electron domain geometry, and we will call the central atom sp hybridized because it needs to hybridize one s orbital and one p orbital in order to make the 2 sp hybrid orbitals to accommodate this bonding pattern. And we will more thoroughly explain this hybridization process just a bit later. For 3 electron domains, 120-degree bond angles would be adopted. This is a trigonal planar electron domain geometry. Here, the central atom is sp2 hybridized, requiring one s orbital and 2 p orbitals to hybridize to generate the necessary hybrid orbitals. With 4 electron domains, we must begin to utilize a third spatial dimension, so it won't be 90-degree bond angles. If 4 domains adopt a tetrahedral geometry, there will be 109.5-degree bond angles, which is substantially larger than 90. Here, the central atom is sp3 hybridized, using all the s and p orbitals in its valence shell to form the necessary hybrid orbitals. Most of the compounds we will discuss will exhibit one of these configurations, but let's briefly mention a few more. With 5 electron domains, we get the trigonal bipyramidal geometry, which has both 90-degree and 120-degree bond angles. And for 6 electron domains, we get something called an octahedral geometry, with all 90-degree angles. Once again, each of these geometries is adopted because it allows for the electron domains to spread out in space as much as physically possible while remaining bound to some central atom. And the number of electron domains determines the number of atomic orbitals that must hybridize to generate the necessary hybrid orbitals to accommodate the bonding. This table summarizes the geometries that are dictated by the number of electron domains that surround a central atom, which correspond to a particular hybridization. But these larger categories can be split up into subcategories if some of the electron domains are lone pairs rather than bonding pairs. This will allow us to make the distinction between electron domain geometry and molecular shape. This describes the placement of only the atoms rather than both atoms and lone pairs. If a molecule has no lone pairs, such as with methane, then the electron domain geometry and the molecular shape will be the same, since all of the electron pairs are covalent bonds that lead to other atoms. We know that this molecule will be sp3 hybridized and therefore tetrahedral, and the way we represent this three-dimensional molecule in 2 dimensions is either with a ball and stick model or with dash and wedge bonds. When we use this notation, the wedge bond implies that the atom is coming towards you, or is closer to you than the plane of the screen, and the dashed bond implies that the atom is going away from you, or is farther away than the screen. If we look at other molecules that have tetrahedral electron domain geometry, we can see that the molecular shape will begin to change as we replace atoms with lone pairs, because the molecular shape is only concerned with the locations of atoms, not lone pairs. Look at ammonia, for example. Nitrogen has 3 bonds to hydrogen atoms and 1 lone pair. That's 4 electron domains, so ammonia is sp3 hybridized and therefore has tetrahedral electron pair geometry. But the lone pair is not included in the molecular shape. We give this molecule a different name when it comes to the molecular shape. We will call it trigonal pyramidal. Let's compare methane and ammonia in order to see that there are similarities in the orientation, as they have similar bond angles, although with ammonia they contract slightly due to the additional repulsion offered by the lone pair. But they certainly have different shapes because of the differing numbers of atoms. We could do the same for a water molecule, which has 2 bonds and 2 lone pairs around the central atom. That means it has 4 electron domains and will be sp3 hybridized, with tetrahedral electron domain geometry. But with 2 lone pairs, we will call the molecular shape bent. The bond angles decrease even more as the second lone pair is added, again because the lone pairs repel other electron density slightly more than bonding pairs, and we should take note of these angles for methane, ammonia, and water. This table will show us all of the molecular structures that are possible within a particular electron pair geometry as we successively replace atoms with lone pairs. The more electron domains there are, the more possible molecular structures there are, because there are more combinations of atoms and lone pairs possible. To make sure we can use VSEPR theory, let's try a few examples. CO2, BCl3, and SF4. First, we must draw the Lewis diagram for each molecule. Those will look like this. Now let's count up the electron domains. The carbon atom has 2 electron domains, that's the 2 oxygen atoms. The boron atom has 3 electron domains, the 3 chlorine atoms, and the sulfur atom has 5. That's the 4 fluorine atoms and the lone pair. We must be able to draw the correct Lewis diagrams in order to have the correct number of electron domains, so make sure you are comfortable with this first. Next, let's assign the correct electron domain geometry on the basis of the number of electron domains. That will be linear, trigonal planar, and trigonal bipyramidal, respectively. Lastly, the molecular shape will be different for any molecule that has lone pairs on the central atom. SF4 is the only one that does, so let's look at that one. With 1 lone pair, we will say that this molecule has a seesaw molecular structure. Now, with molecular geometry understood, we must return to the concept of polarity in order to determine whether a molecule is polar or nonpolar overall. We know that if the difference in electronegativity between 2 atoms is somewhere between around 0.4 and 1.8, they will form a polar covalent bond, in which the electrons are shared but unevenly. The atom with more of the electron density will be partially negative, and the atom with less of the electron density will be partially positive. That bond will have a bond dipole moment, and we can represent that dipole moment with a vector, which is basically an arrow that shows both direction and magnitude, such that a longer arrow means a greater dipole or more polarized bond. These vectors point in the direction of the electron excess. We can see here that a BF bond has a longer dipole vector than a CH bond, because the BF bond is more polar. But we also want to be able to assess whether a whole molecule is polar or nonpolar, because if it is polar, it will have a net dipole moment. We can find the dipole moment of a molecule by adding up all the individual bond dipole moments. If there is a net dipole, the molecule is polar. If there is no net dipole, which can happen either if there are no polar bonds or if the vectors of the individual bond dipoles cancel each other out, the molecule is nonpolar. For diatomic molecules, the net dipole moment is just the individual bond dipole. If the bond is nonpolar, the dipole is zero. If the bond is polar, the dipole is determined by the bond dipole moment. But if we get into larger molecules with 3 or more atoms, we have to take into account the geometry of the molecule to see how the bond dipole moments will add up. Let's compare CO2 and water. These each have polar bonds, whether CO or OH. But CO2 being linear, when we add up its bond dipole moments, they cancel out because they are equal in magnitude and opposite in direction. So CO2 is a nonpolar molecule. Water has a bent molecular shape due to the lone pairs on the oxygen atom that cause it to adopt a tetrahedral geometry, so the individual bond dipole moments point slightly in the same direction. That means when we add them together, there will be a net dipole moment, and therefore water is a polar molecule. If we replace an oxygen atom on CO2 with a sulfur atom, it will become polar because the CS bond has a weaker dipole than the CO bond, so the net dipole will be slightly to the left. Things can cancel out in more than 2 directions as well. BF3 is nonpolar while NH3 is polar. Due to the difference in geometry, trigonal planar versus trigonal pyramidal, meaning the NH bonds all point somewhat in one direction. This can work for 4 directions or more as well, and symmetry will be the key to seeing if this is the case. We can look at methane and replace hydrogen atoms with chlorine atoms one at a time. Methane is nonpolar as there are no polar bonds, but introducing one carbon-chlorine bond, suddenly we have one bond dipole, and thus a net dipole, and thus an overall polarity of a particular magnitude. Introducing another chlorine atom, suddenly the net dipole diminishes slightly as the 2 bond dipoles point in different directions, though the molecule is still polar. Adding a third, this effect is enhanced, though it remains polar. And adding a fourth, all the bond dipoles cancel out and the molecule becomes nonpolar. And finally, as promised, let's return to the concept of hybridization so we can better understand what that means. Looking at BeCl2, the beryllium atom has 2 electron domains, since it has just the 2 covalent bonds and no lone pairs. In order to accommodate these 2 electron domains, it will need to hybridize 2 atomic orbitals. So it will take its 2s orbital and one 2p orbital and hybridize them to form 2 sp hybrid orbitals. These will be equal in shape and energy, and they will have a shape that resembles a combination of the s and p orbitals. These hybrid orbitals will be arranged 180 degrees apart in linear fashion, and each of them can accommodate the 2 electrons necessary to form a covalent bond. The bonds will occur when the sp orbitals overlap with orbitals from the chlorine atoms. Let's see this illustrated in an energy diagram. For an isolated beryllium atom, we can see the 2 valence electrons sitting in the 2s orbital, while the 2p orbitals are empty. But when it hybridizes the 2s and one of the 2p orbitals, we get 2 sp orbitals, which will have an energy that is in between the s and p orbitals, and it will therefore put 1 electron in each according to Hund's rule, so that it can form 2 covalent bonds. Any central atom with just 2 electron domains will exhibit sp hybridization. If there are 3 electron domains around an atom, like there are for boron in this molecule, there need to be 3 hybrid orbitals to accommodate them. So an atom will take an s orbital and 2 of its p orbitals to make 3 sp2 hybrid orbitals. These orbitals will then repel each other so as to generate a trigonal planar geometry. The boron atom will therefore exhibit sp2 hybridization and trigonal planar geometry. Once again, we can compare the orbital diagrams for an isolated boron atom with a full 2s orbital and one p orbital half full, and then for the hybridized boron with sp2 orbitals that are lower in energy than the p orbitals and equal to one another, which is why each one gets one of the 3 electrons. Any atom with 3 electron domains will use sp2 hybrid orbitals. With 4 electron domains, like the 4 bonds around carbon in a molecule of methane, we will need to combine 4 atomic orbitals, so that will be the s and all 3 p orbitals, to get 4 identical sp3 hybrid orbitals. These will adopt the tetrahedral arrangement found in a molecule like methane. For the orbital diagram here, we can see that the s and all 3 p orbitals will be utilized to get the 4 hybrid orbitals, each of which will contain a lone electron and overlap with the 1s orbital from a hydrogen atom to make a CH bond. Let's extend this to look at double and triple bonds. We understand covalent bonds as the overlapping of atomic orbitals. This overlap can occur between atomic orbitals of any type, whether 2 s orbitals between an s and a p orbital, 2 p orbitals, or some combination of hybrid atomic orbitals. When this overlap is a direct overlap, meaning that it happens on the internuclear axis, these will be called sigma bonds, symbolized with a lowercase sigma. In a sigma bond, all the electron density is distributed immediately around this internuclear axis, or the line that could be drawn between the 2 nuclei. In a Lewis diagram, any single covalent bond is a sigma bond. We can also have a lateral or side-by-side overlap of p orbitals. This will be called a pi bond, and it is different from a sigma bond in that the overlapping occurs on either side of the internuclear axis. In a pi bond, the internuclear axis itself will be a node, or a region where there is no probability of finding an electron. In Lewis diagrams, double bonds consist of 1 sigma bond and 1 pi bond, and triple bonds consist of 1 sigma bond and 2 pi bonds. To see how this works with orbitals depicted, let's look at C2H4. There is a double bond between the 2 carbon atoms, which means 1 sigma bond and 1 pi bond. This is because the carbon atoms are sp2 hybridized, having 3 electron domains each, so we have direct overlap of sp2 hybrid orbitals between the carbons, and direct overlap between sp2 hybrid orbitals and the s orbitals of these hydrogen atoms to form all of these sigma bonds. But that means the carbon atoms each have 1 unhybridized p orbital left over, which will jut out on this perpendicular axis. It is the lateral overlap of these p orbitals that generates the pi bond, which is the second covalent bond between the carbon atoms. We can see the same thing for C2H2, which has a triple bond between the carbons. These carbons are sp hybridized, so again the direct overlap between these hybrid orbitals, as well as between the hybrid orbitals and the s orbitals for the hydrogen atoms, will produce the sigma bonds. But with sp hybridization, the carbons each have 2 unhybridized p orbitals left over, which gives us p orbitals on this perpendicular axis and other p orbitals on this other perpendicular axis, leaving us with this propeller-like configuration. The lateral overlap of each of these pairs of p orbitals produces a pi bond, which is how we get 1 sigma bond and 2 pi bonds to get the triple bond. So to summarize, the first bond between 2 atoms will always involve direct orbital overlap to make a sigma bond, and then additional bonds can form if p orbitals participate in lateral overlap, making pi bonds. A pi bond is typically weaker than a sigma bond since there is less orbital overlap than the direct overlap of a sigma bond, but adding pi bonds to a sigma bond will increase the overall bond strength, so a double bond is stronger than a single bond, and a triple bond is stronger still.
And with that, we complete Unit 2, which means we have a thorough understanding of the types of chemical bonds, the structures of ionic solids and metals, as well as Lewis diagrams, VSEPR theory, and hybridization. I'll see you over in Unit 3.